Hi students, this is my demonstration for your freezing point depression lab on the Smart Sparrow for Chem 121. So freezing point is what they call a colligative property, which means that this is a property that doesn't depend on the identity of the substance, just how much of it there is. So freezing point depression and boiling point elevation depend on how much of something there is, and because it depends on how much of something there is, and then we can weigh that stuff, we can usually get the molecular weight of it, which is the mass of it, divided by the moles, because the how much of is generally in terms of moles, which we can solve for, and if we can also weigh it, we can get the molecular weight, which is one way that we use to identify stuff. And that's problematic for salts and things that don't dissolve the way we want to, but anyway, this is how you do it. I'll take you through a little bit of getting the data and a little bit of calculation. So this talks about it a little bit. And so when you do this lab, they talk about the freezing point depression. So this talks about, so things get cooler. This is a time when the phase is the same. It's all liquid. And then there's a phase change so that the temperature is not changing, but the phase, this is an energy of crystallization here. And that stays the same, and then it cools again once it's a solid. And this is it's the freezing point. If you're going this way, it's the melting point if you're going the other way. So, and this talks about this data a little bit. This is the delta TF. That's the change in freezing point. The KFP is the constant, which is a property that is for that solvent. The solvent has to be in much greater amount than the solute for it to be effective. And then this is the molality, because not molarity, anything with temperature changes, you don't want to use molarity, which is moles of solute per liter of solution, not solvent. And the liters change with temperature. So a liter at 25 degrees C is smaller than a liter at 40 degrees C. So for that reason, we use molality, which is moles of solute per kilogram of solvent. And so it's a little bit different than molarity. So there's a practice problem in here, and they show, oh, hey, the freezing point dropped in this case by looks like 10 or something. And they give you an example to go through. We won't do that. I'll let you do that on your own, but I'll take you through some real data. It also talks about this supercooling here, because it gets a little cooler before the crystals start forming, just because it's the solution is still coming to equilibrium, and so this can tell you where the actual point is. And they say, oh, you can extrapolate there, but we don't do that. It tells you to do it, but you can. We're just going to measure it, like say right here, which is slightly lower than the number that you should probably get, but it's a good guesstimate. So anyway, there's your example stuff. Oh, it talks about the Van Hoff factor too, and this is what makes it tough for salts, is because they dissociate. If it's an unknown salt, you don't know into how many moles it dissociates. It's just, so sodium chloride, the Van Hoff factor is 2. For this example here, it's potassium sulfate. It's close to 3. It's not always quite 3, because they never all dissociate, especially depending on the concentration. So it becomes complicated, so we try to stick with things that just have a Van Hoff factor of 1 that don't dissociate, for us anyway. So blah blah, more stuff. We're going to go through and we're going to get the the temperature of the solution, the regular melting point. So what we do is I'm gonna do this, but I'm gonna cut these parts out so you don't have to watch it. I'm going to put the weight boat on here. I'm gonna tear it, and then I'm going to take this guy here, and I'm gonna get 5 grams of the solution. I better make sure it's nice and teared, okay? And then I'm gonna, come on, get there. There you go. Oh, no, it didn't go. Okay. Going to put this right here, and then I'm gonna put 1, 2, 3, 4, 5, and I'm going to then throw this out and close the door and record that number. Or record that number right there. It's not recording. Okay. Oh, it doesn't. Never mind. It doesn't matter for this. This is the first part. So All we got to do is dump it in here, and then we close it, and close this, and we go. And through the magic of movie making, we are already there. And then all we do is click heat off, and we'll start seeing the data collect here. So now through the magic of movie making again, we're back down to normal temperature, and then we can just kind of get an idea. I'm zooming in here to get some kind of idea of what temperature we're looking at. And it looks like I'd say that this little bump right after is what I'm going to call it 50. 50, yeah, it looks about 50, the Y. I think the actual number is like 48.5 for this, but we write down the data we got, not the data that we think ought to be right. We'll go next. I'm going to empty this out. That says I did a good job. Well, that's great. So you have to empty this thing. So click empty. You go next. Then you have to do two trial data things. And so what you're going to do is what I was trying to do earlier on accident is put your dish in here, your weighing dish, tare it, and then you're going to put 5 grams of stuff in there, just like you did before. This time you have to record the mass. Go 1, 2, 3, 4, that's 4, and just 5, and then we're going to put that here, close the door. That's 4, let's see, record that 4.9843. So I'm going to divide that by 1,000 and put it here, 0.0049843 in this spreadsheet, which I'll show you what that's for later. And then we're going to take this and put it in the, put it in the calorimeter. Throw that away. And then I'm going to put another dish in here. Hopefully it weighs about the same, and it does, but not exactly. So I'll tare it. I'm going to go to the next page, and then I'm going to weigh some of my unknown, which is with a fresh scupula, which is our solute. In this case, the benzophenone is the solvent. I say, okay, you little joker, get on that thing right there. Trying to do this. Oh, the door's shut because I'm a dummy. Okay, there we go. Now I do, it says approximately 0.2 grams, so I put those two in there, get rid of this thing, and then I close the door, record 0.1978, so I'm going to record that here, 0.1978, and I'm going to say demo, and I will put this in there too. So I'm going to go here, and we'll do some more movie making magic so you don't have to watch this process. We're going to go next page. We're going to go heat on, watch it heat up. So there we go. You should empty this when you're all done. But let's take a look here and see what the freezing point is now. I'm going to say it's 40, let's call it 47.1, I'd say. So 47.1, and if before it was 50, that means that the freezing point depression was 2.9 degrees. So I'm going to write that here. So, whoops, that's familiar. So that's 2.9 degrees. So in your data table in your thing is your data sheet here. But I just wrote that here in a spreadsheet. This is the numbers spreadsheet in Mac. So I've got my kilograms of solvent was 4.9 times 10 to the minus 3. My mass of solute. This is my data. So these three columns here are, I'm going to put this in a color so you can see it more easily. This is I would call it green, I guess. Well, that's blue. Let's call that blue. The black stuff is calculated. The blue is data we took. So what do we do? So what you got to do is, I'll do this with a pen first, and then I'll show you. So the main thing is that we start with the equation that let's go back to pen here, is that delta TF, the freezing point depression, is equal to the molality, that is times the freezing point constant. And to put this in a little more detail, the freezing point depression is equal to the moles of solute, this is a T, per kilogram of solvent, times, and you have to look this particular number up, but in this case it's 9.80, I believe, and that's degrees Celsius per molal, or per molality. So this way these units cancel. This way the molality here cancels this molality, and you're left with degrees on either side. So what's our first order of business? Well, the first thing we have to do that this lab will require is that you calculate the molality of the solute. So we're going to go ahead and do that. We have the tools we need to do that, because we have the freezing point depression and we have the temperature change. So for us, we just have to, and this is kind of a fun part for me, we just kind of rearrange this equation. We just go whoop-a-doop-a-doo, and we put this over here and divide that by that, and we put a line here. And then, therefore, the change in the temperature, the freezing point temperature, divided by 9.80 degrees Celsius per molality, sorry for my horrible handwriting, it's going to equal the molality of this solution. So that, in our case, is 2.9 degrees Celsius divided by 9.80 degrees Celsius per molal. So that's going to equal, and we look over here on our spreadsheet, that's exactly what we did. I have here, this demo, I got, if you look in here, I have D9 divided by E9, so that's D9 divided by E9. If you look, you got 0.30, so we get 0.30, it's a 0.30 molal. There, that's this part here. So I'm going to go ahead and erase, I'm going to go ahead and erase this stuff up here, and I'm going to scoot that up so we can see it a little better. Okay, and here we go. There we go. All right, sorry about that. I'm going to take this stuff up to here. So we've done that part. Then we need to calculate the moles of solute and then the molecular weight. So the moles of solute we get from, look on our spreadsheet here, I'll show you, we get from F9 times B9. So that is the molality we did, right? Which is moles of solute per kilogram of solution, and then we just multiply it by the kilograms of solvent. So we multiply that by the kilograms of solvent. So easy enough, right? So if the definition of this is 0.30 moles of solute per kilogram of solvent, then if we multiply it by the kilograms of solvent, which in our case was 0.0049843 kilograms of benzophenone, we will get, just because these cancel, right? Because kilograms and kilograms are canceling, we just get moles of the solute, if you can read my perfect handwriting. But it is not easy to draw on these things. And then in that case, we get the number. We get the number in our spreadsheet here, which is 1.47 times 10 to the minus 3. So that number will be 1.47 times 10 to the minus 3 moles of solute. So since we know that molecular weight has a definition of grams per mole of anything, we just take the grams of our solute divided by the moles of our solute. So we already have the moles, so we just say the molecular weight here is equal to this guy, which I'll just capture that, put him here. We already got him calculated, so he's going to go down here, literally down there. And then the make this a little longer. Whoops, make this a little longer. Right here. So the grams of solute was from our lab. I'll bring that back over here. We got grams here. This time it's grams, not kilograms. 0.1978. So we have 0.1978 grams of solute. Since these are both solute, that part cancels. We get grams per mole. Whatever answer we get, grams per mole, which is a unit from the periodic table. And the answer in this particular case is equal to 3 significant figures. So we get 134 grams per mole is the answer to this one. We'll do it a couple times. You'll probably get something between 131 and like 137 the second time. And whatever we have, whatever we put in here, has a molecular weight of about 130-ish. That's how we find it. So that's how you do it. Good luck and have fun. Take care. Bye-bye.